All right. Well, happy Tuesday. So first thing first, again, Chrome is just garbage. Um, again, so billions of data records that were collected from incognito mode are now getting removed thanks to a lawsuit against Google because they suck. I mean, they gave it to us for free, but not being actually incognito and still collecting data for selling it and all those sorts of things is, not, don't be evil or whatever they're. So I did post this one in the Discord if you want. But again, just it's garbage. Anyway, so moving on. So we've got to talk about Project 3 and then searching and sorting from Chapter 14. And then I've got a small little change to the schedule. Unfortunately, Thursday morning I can't be here. My son's robotics team made it to the state championship. So we'll be out in Saginaw Valley for Thursday for the first robotics. Should be a lot of fun. I'll miss you guys, but watching, I mean, they're not as cool as BattleBots, but they're still, robots are fun.
I was going to ask if it was BattleBots or
no, just the first stuff. So they have to pick things up and throw them places and do those sorts of things. But that should be fun. So we'll miss you on the 4th. But I think we can get close to most of searching and sorting done today. If we don't finish all of it, we can save it for 4.9 because we'll have a little bit of time for streams and ethics that won't take us the entire amount of time. And then so just take 4.4 to work on the group project then. We can just have that whole hour 15 in the morning to work in the group because I'm sure everyone wants to spend an hour 15 at 9:30 in the morning working on the group project with their partner, right?
Now, is it still a group project, or is it like you can work on it on your own?
Yeah, if you'd like to do it yourself, you can. For some reason, this is not the same as my other 200 or 2001 class that does have an outcome of working in a team. And I don't know how that happened. I'm a little confused. I thought we used to be part of a team, but this is the latest and greatest set of outcomes. So if you'd like to work with a partner, great. If not, you work on it yourself. You will have group work later, eventually. So. Which is good. So it is actually very lonely to be a programmer who doesn't work on a team. And most of the time, hopefully you'll be on a team and working with people. Honestly, one of the best pieces of advice I ever got was don't be the smartest one. Like that, you will learn and grow and be a better programmer if you're not the smartest one in the room. So working on a team with people who know more than you helps you advance better and grow better and be a better developer. So those sorts of things are great. And fresh out of school, hopefully you've got some senior devs you can talk with that can help you debug things and figure things out. And having 20 plus years experience does give you an advantage. Go figure. So that sort of thing. So group work is a lot of fun. You don't always get to pick your teams in the real world. You don't always get to pick your teams in school. That sort of stuff happens, but generally, if people suck, they don't end up working there for long. That's not always the rule, but generally you get to work with some pretty decent people. Is how that works. So, all right, so let's talk about the project. Let me fire up Visual Studio. How'd this one go for you? Our stacks and queues. Easier than checkers? Harder than checkers?
Easier.
Easier? Okay.
I think thinking around the numbers was probably the most challenging part, but actually using stacks and queues was not that challenging since we didn't have to write our own.
Yeah, that's not, I think just getting through the input is probably the weirdest part of this one here. So this is Project 3. All right. And again, part of your points here were from object-oriented design using classes. So classes should be independent of the input. Right? My class shouldn't depend on you to type something in the screen. If a class needs some information, you need to pass it to it as just the information it needs. So that it could be a console app, it could be a graphical app, it could be a web app, it could be a mobile app, those sorts of things. We want to make our classes independent of that. So the business logic is still the business logic, no matter where the input comes from. So that's how I'm going to build my classes. Again, as long as it's not just one big main method, I'll give you some points here. Not super concerned. But if it's all in main, right, that is not using classes at all. That was part of the idea here. Now that we know how to use classes, we're going to use them for everything. Right? Helps us separate our concerns and things. And then make sure we do the calculations right. without stacks and queues, and then actually points for using stacks and queue, or a queue of stacks and queue here. Was some points for that one. Okay. So the first thing I'm going to do then is I'm going to write my class. So I think the easiest one to take care of first was kind of like the doc. So if you think of where everything's going to go, right, that was all going to kind of go on this doc. The doc is going to have a private section and a public section here. So things that the doc had is it has this queue of integers for the plane. It has the plane items, right? So I want to include namespace standard, include, oh my goodness, which one? Queue? Is that the one? You can make a queue of integers for my plane items, right? And then we wanted a stack as well. Include stack. Now, the train items, we're going in a queue of stacks of train items, right? Because we're going to stack them 5 high. So this will be a queue of stack of integer here for my train items. Okay, this is where I'm going to store all my train items. Okay, and then other things I want here. So we could use classes for trains, we could use classes for planes, right, to represent these, because trains and planes know something about themselves, right? They know how many items they need until they're full, and they know what time they were full, right? And they probably know how many items they currently have as we start loading them, and maybe they know what their train number is, and again, depending on how we design this, maybe they know how long it takes to get there and back. That's sort of a useful piece of information here. So I'm going to have another class in here. Let's start with train and see how this goes, right? So if I write a class for train with a private section and a public section. So we said we know a couple things here. We had an int for the number of items until full, and then a current number of items, and then what else do we have? Like what number it was? I don't know if that's actually going to be useful or not. Maybe we had the minutes for a one-way trip. Minutes for a one-way trip, maybe? Does that seem like a value we'd probably have? So you can make it these trains then, and I could have a train constructor that takes all these things here. So it would take the number of items until full, and it would take the minutes for one-way trip. Right. It's going to start off with 0 items here. So my current number of items is 0. My this number of items until full. Oh, this is the number of items until full, and my this minutes for one-way trip is the minutes for one-way trip. Right. So then in my doc, I can have probably a vector is probably easy of trains. Right. So I can include vector, and I'll just have a vector of trains. So I want to include train, right? I'm going to go in here, so we're going to include train, train, and I can have a vector of type train for my trains, right? So this will be my list of trains that I have going. And then if I make another class for plane, I pretty much should copy paste this, right? There's not really anything different for plane versus train here. So you don't want to have the same code twice, otherwise you should feel bad about yourself, right? And we don't want to do that. So why don't we just call this like something else? What's something a little bit more generic, like transport method? Here, we'll rename it here, transport method. I'm going to rename this one to transport method. Okay. So now I have a transport method. Oh, I didn't rename my include there. That's sad, but that's fine. For train, and then I'll have a vector of transport methods. Transport methods for planes, right? A list of planes, a list of trains. Okay, so now to make a doc then, I need to give it all these values. Now, the first line doesn't actually matter at all to me, because unless I want to do some checking to make sure I have the right number of numbers, if I have a vector, I just keep adding. I don't need to pre-size it at all. I could, I guess. I could say, hey, I've got a vector of size 3 and a vector of size 2 for planes and trains. If we're only going like to 110, we're probably not going to gain a whole lot of speed by pre-sizing here, right? Sure, it is one thing we can optimize, but at this point we probably don't care. So I'm going to ignore the first line and say I just need 4 pieces of information. I need the train number of items for trains. I need the number of items per plane. And then I need the train items and I need the plane items, right? So I want like 4 vectors of integers, essentially. And if I'm not dealing with input, I don't need to take them as strings and do any sort of weird splitting or do any of that stuff. I can say, hey, give me a vector of ints, right? Whatever manages the user input will be responsible for converting that to a vector of integers for me. Right? So we can make it as easy as we want it here. So this will be my doc then. We'll take a vector of integers for the number of items for trains, or what, number of items per train, and a vector of int for the number of items per plane, and then it'll take a vector of int for the train items, and a vector of int for the plane items. Right? Just take all those values. So for the number of items per train, I'm just going to make a new train for each one of those things and throw it into my train here. Right? So for int number of items, I don't know, in my number of items per train, I'm going to take my trains, I'm going to push back a transport method. And the transport method needs, for my constructor, the number of items to hold. That's the number of items. And then the minutes for the one-way trip. Now, this one, right, for a one-way trip is just the train number. So for the first train it's 1, the second train it's 2, the next train it's 3, on and on and on. So I might, instead of actually using this sort of loop, if I do an index-based loop, I can just use the index. Right? So I can say for index is, I can even start at 1 if I wanted, right? And then index is less than or equal to my train items dot length. Okay, that's getting ugly. We'll just do 0. My train items dot size index plus plus. This will be my number of items per train dot at the index then, and this will be the index plus 1. So when index is 0, is train 1, it's 1 minute. When index is 2, when index is 1 plus 1 is 2, it's train number 2. Right? We can do it that way and just kind of offset them. Does that seem to work? Probably. All right, and then we'll do the same for my number of items per plane here. I'm going to take my planes, push back a transport method with number of items per plane at the index. And now this one now is times 5, right? Because they're planes here. So 5 minutes for a one-way trip, right, for each one of those. So now I've got my trains and planes ready to go, loaded up. Then I need to set up my train items and my plane items. Right? So to do my train items, then I'm going to work through each train item here. So we can say I need to make a stack to put into the queue of stacks for my train items. Right? So I'll have a stack of int for train items, or I don't know, train item stack. And then for int train item in train items. If my stack is not full, let's add to it. Right? If the stack is full, I need to make a new stack. So I'm going to check first. I'm going to say, hey, if my train item stack dot size is equal to 5, I'm going to take my train item stack and push it onto my train items. Take my train items, and I'm going to push back the train item stack, and then I'll make train item stack. Why is it not? Doesn't want to push back stack of int. Train items. Oh, yeah. I have 2 things named train items. This train items, yeah, and then it's just push, right? Push, thank you. So my this train items is my queue of stacks. I'm going to push the train item stack. And then this one then will be a new stack. Oh, I need to reset that one, shoot. Do it this way again. Make a new train item stack. Right? So if the size was 5, excuse me, add it to the queue. Otherwise then, right, if it's not, I'm just take my train item stack, push the train item. That should be inside that curly brace. There we go. Inside this for loop for train items. Right, and then when I'm done, push the stack. So the example had an even number of 5, but nothing says that we had to have exactly 5 items, right? We're going to have somewhere between what was this second one here? Goodness. Total number of trains. Yes, so less than or equal to the number of trains? I don't know, like 100 items, right? T, trains, planes, number of items for trains. I think that was the wrong thing, but not gonna have tons of items, right? It doesn't see exactly 5. So when I'm done, if I push an empty stack back on there, it's fine. I don't care if it's an empty stack. But I want to make sure I don't have like 3 items on a stack. They could just get left off if I have, 8 items for trains. That's the last piece here. And then to put things into my planes, plane items queue, that one's pretty straightforward. So for int plane item, in plane items, take my this plane items, enqueue, oh no, we're gonna in place, sure, because that makes sense, plane item. We'll then place our plane item. That just goes right in the queue. So that one's all ready to go. All right, so by the time my constructor's done, I've set up my vector of trains, I've set up my vector of planes, I've set up my queue of plane items, and I've set up my queue of stacks of train items. Right? And then maybe I'll add a function here for load. So now this probably should return something. Actually, I'm going to return this as a string. We'll say I'm going to return a string value here for load. Let me include string for load. Now to load something, right, I probably need my transport method to be able to let me load, right? So if transport method then lets me load, because it will take the number of items here. Now for it to know when it's full time until full, oh, I forgot to add that one, so this is time until fully loaded. Right, we should probably start that one off at 0 until we know otherwise. Right, so we'll say load item takes an int for current time. So we'll take my current number of items plus, and if my current number of items is equal to the number of items until full, we'll say my time until fully loaded is the current time plus my minutes for one-way trip. And when I'm done, I'm going to return my current time plus the minutes for one-way trip times 2. Right? I'll give back the value of, hey, here's the time that it took the worker to get back here. Because I know what time it was, I'll tell you what time it gets back. Again, maybe that doesn't necessarily work super well in transport method. It'll work well enough for the way we're going to use this here, because you have to tell it what time the worker got there anyway. So if we already know that, I think it makes sense for us to just give that time back, but either one should be okay here. Why is it not like my semicolon now? Where's my curly brace? Curly brace. Yeah? No? Really? Did I miss a semicolon somewhere? Okay, I just hit save and it went away, so that's fine. All right, so when we go to load things then, right? So while my train items, this train items, oh no, yeah, I don't need that one. So while train items dot empty, and while not empty, right? As long as I have something in here to work, I want to start loading trains, right? So then my stack then, so my stack of int is the current stack, will be my train items dot pop. We'll pop off the item here. What? Train items dot. oh, we need the front, sorry, front. And then I can take my train items dot pop, get rid of it, train items dot pop. And while my current stack dot empty, while it's not empty, start working that stack, right? So as long as the queue's not empty, grab the front stack, and as long as that stack's not empty, let's keep working it now. So I'm going to start with the current time is 0, and then I can say current time. We'll take the probably the destination is whatever's on top, right? That's the train we're going to send to. So int train train number will be my current stack dot pop dot top. Grab what's on top, take my current stack, pop it off. So now I grab the top item, and I'm going to go to that train. Now, this is the train number, right? The vector, the index that it's in is going to be -1. So train number 1 will be at vector's index 0. So I just need to take 1 away from that. So then I'll say my trains dot at the train number -1, load item, and we'll say here's the current time. And then I'm going to reset current time, right, to whatever I get back from that. So current time will change to whatever I get back from my load item, which will train number 1 will take 2 minutes to get there and back. Train number 2 will take 4 minutes to get there and back, because this one is tracking that for me. And I just keep on going as long as the stack isn't empty. When the stack is empty, I go back up and grab the next stack off the queue. And I keep on going until the queue is empty. That was it for loading trains, right? Pull the item off the top and keep on loading it. Then I'm going to do the same for planes, right? But this one's a little easier. So while my plane items empty, not, right? Well, it's not empty. Let's take the int for the plane number. Here's my plane items dot front, and then take my plane items, pop off the value here, and I'm going to go to my planes at the plane number -1. Right, and so I need to reset current time back to 0 for my planes here. We'll equal that one dot load item given the current time. Just working the queue. When that one's all done, then now I can give my output. Right, I was going to return this as a string, so the string then should be all the plane values and then all the train values. I'm sorry, all the train values and all the plane values. So trains first. So then for train and train, right? Transport method, train and trains. I need some sort of string for my result here, right? So my string for results or timings or something, I don't know, timings. Starts as an empty string, I'll take my timings. I'm going to add to it my, train dot, I need a way to get that value back out, right? I need time until fully loaded. So int get time until fully loaded, return my time until fully loaded. So train dot get time until fully loaded. And I need that as a string, right? This is integer to string. Int to string. Int string. Oh my goodness. It will just let me? I don't know if it'll just let me add to my string. It might. And then probably add in a space here to separate it with spaces so it looks a little bit prettier. And then when that one's all done, then I can add a new line, my timings, add in there the new line character, and then do it again for planes, for plane and planes. Plane get time until fully loaded, separate them all out, and then I can return my timings. Right? So load them all up, get the timings. So then somewhere in main here, then at some point, if I have all these vectors of values here, so I'll have a vector, this is my int here for train items, or items, number of items per train. You include vector, and use my namespace. So vector int for this is my number of items for trains. was that 3, 2, and 7 and 2 or 1? 2, 7, 1? That sounds right. 2, 7, 1. Yep. And then number of items for planes. Trains, that was just 3 and 2. And then a vector of int for my train items. This one here. I go ahead and add some commas. Don't need the last one there. And then a vector of int for plane items. Is it 2, 1, 1, 2, 1? 2, 1, 1, 2, 1. And I can make a doc. So I need to include doc. I can make a doc. Doc. Given all those values, right? Here's my number of items for trains. Here's my number of items for planes. Here's my train items. Here's my plane items. And then I want to load, right? Doc.load, and I'm just going to output that, right? Because I get back a string from load. I can just be able to output it. Should we try it? Let's see. Oh, it crashed. Okay. All right, we're close. So index out of range. Right, so we were at where here? Doc trains pushback. How did that train items dot size? What is number of items per train? Oh, I used the wrong one. So this is my train item size. I don't want the train items size, right? This should be my number of items per train size, right? Because I was doing that wrong. All right, let's try that again. Oh, okay, another one. Let's see, where's this one here? Same one? Index out of bounds, really? Trains, size is 3. Pushing back, number of items per train, size is 3. I didn't have a less than. I just say size. So this loop never stops. This is index is less than. Wow, that's funny. It lets me type that. Index is less than the number of train items dot size. It'd be nice to stop my loop at some point. Invalid vector subscript. That didn't look right. Train. Let's see if we get to here. I'll put a breakpoint in. All right, we didn't crash yet, so I think we've got like this for trains. Minutes until fully loaded was 9. Time until fully loaded was 9. Time until fully loaded was 12. Time until fully loaded was 3. These values don't seem right, but they should have come out as values, right? My timing string is bad. View. Is it nothing here? Why is there no value? I think I have to convert this to a string. C++, int to string. I can't remember how to do this. To string, okay. Thought it was something like that, to string. To string, let's try that. We're getting close. Just keep running. We get an output? Hey, okay. So we got some numbers, but they're wrong. So we're getting close then. Right? So we got 3 was right, but 9 and 12 are not right here. So what's up with timing? Current time is, why is that not giving me the right value back out? Current time, oh, the current number of items plus the one-way trip. That's not what I want to return. I want to return the current time. That ought to do it. Okay, those numbers look better. So a couple bugs, right? Not too bad, not too shabby. That makes sense? All right, cool. Let me go ahead and commit this one here. Here, project 3. Commit and push. All right, again, yours might look way different. That's okay, right? Different ways of using classes, perfectly fine. Whatever makes sense to you, as long as you don't just have one big main method. Right? That was the goal here. Right? You want that to be separate. So if this is going to deal with input grade, I didn't even deal with any input because I didn't care to. Right? There was no points for dealing with input, so you can just give it values any way you want here. Sorry, what is wrong with my sugar? Donuts for breakfast are bad for my sugar. Who knew? Let's try a little more insulin. They are tasty, though. All right. All right, should we move on to new stuff? New project. This is, what week are we in here now? Is this week 12? 13? Let's see. Week 13. Wow, we are almost done, friends. Week 13. 13, searching and sorting. All right, and using namespace, standard. Why? All right, the red went away when I hit run, so that's fine. I think my Visual Studio is just really confused right now. And let's find our Zybooks here. So we're not going to get super deep into these ones here. Okay, the big piece we're looking at is now we got to start looking at how things are fast and slow, right? We spent some time doing that with stacks and queues. So it's all based on this O notation for searching and sorting. So again, we're going to come back to how fast are these things and how slow are these things. So if you imagine looking through a list here and finding, hey, what is the smallest item in a list? Right? You have to look at every single value. So that would take n operations to find the smallest value. If it's a sorted list, if the list is already sorted, to find the smallest one is going to be super fast because you know it's at the front, right? The smallest item would be at the front here. So if it's sorted, finding that's easy. If you want to find a value in an unsorted list, you have to look at every single value. If I just give you a bunch of numbers and say, hey, is 27 in there? Or in this case, hey, is 11 in there? You have to look at every single value. It's like n operations. If the list is sorted, we can be a little bit faster, right? Because like when you play the number guessing game, you split the difference every time. You look in the middle. And then if it's too high or too low, you look in the next half, and the next half, and the next half. So that gives us a quick way of looking through a sorted list here. So if I give you a sorted vector here, we can do a, so it'll probably be like a Boolean value of yes or no. It's in here, you know, contains, given a vector of a int for, let's include vector, This is a sorted list here, and then the int value to find. Right, and we'll do in contains in sorted list. That might be easier here. And I can just call this my list. Or maybe we'll just call that numbers. How about that? This will be numbers. Contains in unsorted list. So if it's in an unsorted list, I just have to look at every single one. So for int number in numbers, if the number is equal to the value defined, return true. If we've looked at all of them and we haven't found it, we're going to return false. Right? So then this would take O of n operations, right? Has to check all n values. But in a sorted list, we can save a little bit of time here. Right? So in a sorted list, we're going to find the middle, right? And then split the difference. If we're too high, we know we need to go to the other side. If we're too low, go to the other side, right? As we go. So you can do this one of two ways. You can do it iteratively or you can do it recursively. Right? Iteratively will perform better, but recursively is pretty easy, right? So if we write another bool, this will be our contains in sorted list given a vector of int for numbers, given the int value defined, given an int start index and an int end index. Right? So all we're going to do then is we're going to return our contains value in sorted list given the numbers, given the value defined, given start at 0, numbers, there we go. And this will be my numbers.size -1. Right? So here's the beginning, here's the end. Start at the beginning, start at the end. So this one then, we can check. We need to find the middle. So the middle index will be the end index minus the start index divided by 2. Right? Find the middle of those 2 points. And make sure I do some order of operations here so I don't screw this up, right? Now, integer division here is good, right? I want an integer result back out. That should work out pretty well. And I can say, hey, if the value defined is equal to my numbers at the middle index, we're going to return true. If I didn't find it, then I can say, hey, if the value defined is less than the numbers at the middle index. So if it's less than that, it must be on the left-hand side. I'm going to return contains the numbers, the value defined. I'm going to start at the start index. That one stays the same, but then the end will be middle index -1. Right? I already checked the middle, so go one less than that. Right? And if it's not that one, then I can return go one larger. So start at the middle +1 and go to the end. Right? Eventually these ones should match. Right? Oh, it's plus here, I'm sorry. I think it's plus. I add them together to find the middle, not subtract. Right? Because if I want like 5 and 10, if I'm looking in the second half, 15, divide that in half, I should get 7. 7 should be the midpoint between 5 and 10. Right? To find the middle index. If I get down to the point, oh, this is middle index here, where they're the same value, then I need to be done, right? So I've only had a base case if I found it here, but if I keep getting down to the same point here, I haven't found it yet, I need to be all done, right? So if start and end are the same value, and it's not there, I need to return false, right? So I can say else if maybe my my start index is equal to the end index, and I didn't return a true, I can return false. Right? Because if I matched here, and I didn't already return a true, it's got to be false. So this is kind of my other base case of not found. Here's a base case of did find, right? If it's not one of those, then right? Search higher or search lower. Now what's cool with this one here is because we're dividing in half every time, we get logarithmic performance. Right? You could have a million numbers and you cut it in half and cut it in half and cut it in half, cut it in half. So this should work in O of log n performance here, assuming we have a sorted list. If you don't have a sorted list, it doesn't work. Right? But if we have a sorted list, it should work. So if we make a list of numbers here, vector of int, for sorted list, and let's throw out some numbers in like some sort of sorted order. So just give me small numbers and get bigger and bigger and bigger. Let's get like 10 numbers. 1, 2, 3, 4, 5. All right, a couple more. 6, 7, 8, 9. All right, easy. 8, 9. I can't get my commas in the right spot. Okay, there we go. So I should be able to get back a true or false if I have a value here. So we'll check to see, let's see out for contains in the sorted list Here's my sorted list, and let's find 2. Right, let's try a couple values here. 2 and 6 and 11. Let's also try a 0, right? So one that's too low, 2 that are in there, 1 that is too high. So it should be false, true, true, false, or 0, 1, 1, 0. Probably need some, oh, yep, if I didn't add the end lines though to make it prettier. End line, end line, end line, end line. What?
Oh, missing a parenthesis for the end line.
I am. Goodness, thank you. All right, didn't find it, did find it, did find it, didn't find it. Looks good so far, right? I think that worked for us. Pretty cool. Awesome. So then in an unsorted list, right, I think, do we even need to run that one? That should just work, right? But it's just a little slower here. So doing some basic searching, a linear search or a binary search works out pretty well for us here. Let's go back to 14. That's our binary search. You just split the difference, right? You don't need to use recursion, but recursion's fine. If you don't want to use recursion, right, it's just a loop, right? It's just a while loop. Same idea here, right? And eventually you don't return it, right? Okay, so we can do that one. That's the binary search. That's our O notation. To sort, we're going to skip quick sort and merge sort. You'll get into those later, but the selection sort and it's merge sort's kind of fun. I guess we can talk about that one. Quick sort we'll skip here, but selection sort and then insertion sort are 2 basic sorts that perform terribly. But that's okay. We're not doing the fast ones here. So a selection sort. So if we want to do a selection sort here, so we would take a vector, or this will just be a void, be a vector of int. Nope, sorry. Void. This is selection sort given a vector of int for numbers. And again, you can sort anything here, but integers are really easy for us. Anything you can compare less than on will work. You can sort, right? As long as you know, is this one less than this one? We can sort it. With a selection sort, what we're going to do is we're going to go through and find the smallest item and put it at the front. So we're going to build a sorted section here as we go. So let me just draw a picture of this one here, because this one's kind of fun. So just throw out some numbers here in an unsorted value, unsorted list.
13.
13,
5.
5,
7.
7,
26.
and 26. Okay. So this is my vector here. To do a selection sort, I'm going to find the smallest value and put it here. So it's going to look at every value in the list, right? Look at n items and say, oh, is this the smallest? Is this the smallest? Is this the smallest? Is this the smallest? And then swap it in this current location. So I'll swap the 5 and 13. 5 and 13 swap. So it says, okay, now this is the sorted portion of the list. This is the unsorted portion of the list. And it looks for the next value. Starting here, find the smallest value. So again, n minus 1 operations now. Okay, so it finds the 7. It swaps the 7 and the 13. So we swap out the 7 and the 13. Now, 5 and 7 are the sorted portion. 13 and 26 are the unsorted portion. It's going to start here at n minus 2, look at all n items to find the next smallest. It doesn't have to do any sort of swapping. Sure, it's done. And then once it gets to the last item, it knows it's already sorted. There's no work to do because we've already put everything that's smaller in place here. So n minus 1, n minus 2, n minus 3, n minus 4, n minus 5. You know, if I've got 100 items here, when you add all that together, right, you get n squared performance. Right, thanks to your math. You remember that? That was a Calc 2, I think. You did that? Probably like that. So this will be a very slow operation here. This is an O of n squared. Right. So we have an int for the sorted index is 0, and an int for the unsorted index is 1. Right. So start here and keep on going. Or that'll always, I guess that'll always be +1 here. That'll be easy. So we'll say for int index Oh yeah, we don't even need to do this here. I'm sorry. So for int, this is the sorted index is 0. The sorted index is less than numbers.size. My sorted index plus plus. Now my smallest item, I'm going to assume is the first thing I see until I know otherwise. So my int smallest number, smallest value index, then it will equal the sorted index. And this one actually I want to go up to -1. I don't need to go all the way, right? I don't need to check the very last one. So the smallest value item is the smallest until I know otherwise, and then now I'm going to loop again. So for int current index is my smallest, the sorted index +1. So start at wherever I was +1, right? Because I need to look at the next n-1 items here. We'll take the current index is less than the numbers.size, current index plus plus. If the numbers at the current index is less than the numbers at the smallest item index, smallest value index, then my smallest value index is the current index. Right? If I find something smaller, know where that is. Right? And I'm doing this by index location because I need to swap these. When I'm done looking through every single n-1 items here, then I'll do a swap. So I'll say an int temp is my numbers at the smallest item index, and then my numbers at the smallest value index is equal to the numbers at the sorted index, and then the numbers at the sorted index will equal temp. Right? What was the smallest value, put at the beginning. I'm sorry, so what was the smallest value? Put where I just was, and put that value back in the smallest. Right? So grab the smallest number here, and then swap it with wherever that current sorted index was. And this one will work its way all the way up to the end. And we're done, it should be sorted here. So if I give it an unsorted list, then a vector of integers, what do we have? Numbers, what'd you say, 13, 7, 26, and 5? We'll call a selection sort, given numbers, and then for int number in numbers, see out the number at an end line. So it should be sorted then, right? For this, selections. Oh, I have a copy here. Sorry, I need to pass this by reference. So I'm actually changing the original one, so I don't change the copy. There we go, 5, 7, 13, 26. That one worked for selection sort. So no matter what happens with a selection sort, I still have to look at n-squared values. Right? You can do a little bit better here with an insertion sort. So we can write an insertion sort given a vector of int for numbers. Now an insertion sort is essentially the same thing but done in reverse. So instead of making the sorted section bigger and bigger and bigger and finding the smallest one each time, what we're going to do is take the value and move it backwards into the sorted position. So if we have the same values here, we had 13, we had 5, 7, and 26, right? So we're going to say, okay, this we know is already sorted. One value is in sorted position. Then I'm going to look at the next value, and I'm going to, if it's less than, I'm going to swap it. So if 5 is less than 13, we're going to swap. So we'll say, okay, let's swap 5 and 13. Done. This is my sorted portion. Right? I got back to the beginning. Now there's nothing before it, so we're done. Now I'm going to swap. Look at the next one. So 7 is 7 less than 13. Yes, it is. So we're going to swap. So we're going to swap 7 and 13. And it says, okay, are you less than the value before you? No, we're not. So we're done. Right? You either hit index 0 or you're no longer less than. That one's done. And 26, we get to 26. It's not less than 13. Nothing has to happen. So this one's done. So what's cool about this one, again, it's still on average will be n-squared, but If you already give it a sorted list, it only takes n operations. It looks at the value, says you're not less than, go to the next one. You're not less than, go to the next one. You're not less than, go to the next one. You're not less than, go to the next one. So the best case performance, if you give it a sorted list, is O of n, right? With the best case performance of our selection sort, it's still always going to be n squared, because you have to look at n items to find the smallest one. It doesn't say, oh, do you need to swap with the thing before you? It has to look at every n minus 1 items, n minus 2 items, n minus 3 items every time. So it's still, on average, is O of n squared, but a best case of O of n. So with the insertion sort, we're going to start looping. So the current index starts off at 1, and we're going to go until the current index is less than my numbers.size. Oh, and this should be passed by reference here. We'll take our current index plus plus. So starting at 1, we need to see, do you need to swap? So we're going to go do this loop backwards now, right? So now we'll say for index to check is equal to the current index minus 1, right? And we'll do while the current index to check is greater than 0, right? Because once we hit 0, we're done. There's nothing less than us. Actually, I think we want, yeah, it's greater than 0, because 0 will be no good here. There's not one less than that. Then my index to check minus minus, right? We start moving these things to the left. So if my value, numbers dot at the current index, is less than the numbers at the index to check, then we need to start swapping here. Right, so then we'll take our int temp is the numbers at the current index, and then we'll take our numbers at the current index, and we'll assign it the numbers at the index to check, and we'll take the numbers index to check and give it temp. Right? So do a little swap. Why is the highlighting so off? My Visual Studio is just upset today. So we'll bump it down by 1. And oh, this should, oh shoot, this needs to be index to check minus 1. Sorry. If it's less than the index to check minus 1. Index to check minus 1. Check minus 1. Because I want, this should just keep on moving as long as we're less than. Right? And then if it is not less than, we can just stop. We can break that loop. Right? This loop no longer needs to run if this is not true. Right? Or really, we could put this in, you can have more than one and check in your for loop. That gets a little silly. I don't really love that, but I think that'll work for us too, because that way the for loop will stop. We don't need to use break, because I think breaks are dumb too. So we'll say, okay, as long as we're greater than 0 and we're less than the value before us, right? Then we should swap and just keep on going, keep on swapping, keep on swapping, keep on swapping. So we should be able to also do then an insertion sort, given numbers. Let's try that. 7, 13, 20. Oh, we didn't get 5. Oh. Why didn't we get 5? Current index is less than size. If we're less than... Oh, no, we want current index... I think we just start at current index. There we go. Just start at the current index. There we go. 5, 7, 13, 26. So start at this one, because this way we get all the way to the end. There we go. All right, so we did the 2 basic sorts, the selection sort, the insertion sort. The quick sort's fun and all. You can read more about that one later. Merge sort is fun in that this one is recursive. So this does a little divide and conquer, which is fun. So it takes a big list and splits it in half, 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 and then puts them back together in a sorted order. I think this picture is fun, right? So we'll see, hey, here's my list of values. So here's the start and here's the end. So I have a middle point. So I'm going to split off the middle point and split them in 2 pieces. And I've got 2 shorter lists. I'm going to do the same with my shorter lists. Split them in half. Go to the next step. Sort those ones. So it's a recursive piece here, which is fun. So this is why we love recursion. You see it lots of places. So split that one in half. Split the next one in half. Right. Now that we've gotten down to size of 1, we can put them back together now. Because you know when there's only one item, it's already sorted. We're done. We just start putting them back together. Now we're going to compare them and say, okay, what order do we go in? Where does this one go? Right, we merge them back together. So when these ones get merged, then merge those, merge those. So you know when you're merging 2 sorted lists, it goes pretty quick. You say start at the beginning of this one, start at the beginning of this one, take the value that's less, and then move that one by 1. Take the value that's less, move that one by 1. So you only have to look at the values one at a time here as we go. There's not a whole lot of comparisons that happen. It goes pretty quick when we merge them together. You make those partitions. So the code's not crazy for it to do a merge sort. I hate I, J, and K. Those are just awful. It's terrible variable names. I hate how they do this. Right? Use something more useful. Right? So it doesn't need to be recursive. Right? You can do it with while loops, or you can also write it recursively. Right? So this one is doing my, I don't think it's, is it calling merge again? I don't think it's calling merge again. Right? So this will be more efficient this way without using recursion. But recursively, it's actually super quick looking, right? We just say, okay, merge sort. If we're less than, again, I and K are just stupid values here. Find the midpoint, recurse. Find the midpoint on the other side, recurse the other direction, right? Keep on splitting, keep on splitting, keep on splitting. Our base case was if we're less than. Once our indexes are the same, we know we're size 1. We're done, right? So merge sort, merge sort, merge sort, and then we merge together. So the merge piece is putting them back together. Merge sort is the recursive piece. Merging puts them back together, right? We just put them all, here's how I put the pieces back together for these ones here. That one goes pretty well. So this is a very common way of sorting things here. When you do it the right way, it's n log n, which is better than n squared. So n times log of n. So it's not super, there's not a lot of ways to sort things super quick. So there's lots of fun ways to sort. These are fun. You'll get into all sorts of different ways to sort here. My favorite one, though, to look at, this is the sound of sorting. Let's see, do they have it on? Here we go. This one is amazing. Oh, and they've got the code for it here, but it essentially puts it to sound as you go. I don't think I can play another YouTube video if I'm going to also put this on YouTube and not get muted. That'll be bad. But if you go check this one out, that's really cool. There's a really cool sort called the radix sort. It's one of my favorite sorts here because it doesn't ever compare values of saying, is this value less than another value? Which is a super fun way to think about it. So it uses buckets. And you can go look that up if you're curious. You'll get into that next class as well. But this one's a fun one to look at. So, all right, that actually went well. I think we got through all the searching and sorting we wanted to. So we'll work on a lab exercise later this afternoon. It'll be a pretty quick one here. We're going to do sorting on things that aren't integers for practice. Right? Should be a lot of fun. Or we can write a class that, as long as we have a less than function, can be sorted. Right? So you can write a sort of type T, a template function. Right? As long as we can compare that to type T with a less than, we're good to go. Right? We don't care what it is. It doesn't have to be integers. Right? So that'll be the exercise we're working on for lab. Okay? So again, I won't be here 4-4. So take that time to work on the final project. If you got questions, let me know. Just shoot them over my way. I'll do what I can. And then, so I'll see you for lab. And then back on 4-9, we'll talk about streams. That'll probably take all of 4-9 for streams, and then we'll get into ethics on probably 4-11. We should be good after that, okay? And then all of week 15 is group project, final project time. If you want to show up, ask me questions during lecture time, great. If you want to show up during lab time, ask me questions, great. I think we'll be able to do the lab just fine. Maybe we'll do a short ethics lab that day, but that'll be short on 4/16. And then all working towards an 8 a.m. final project presentations on April 23rd. That's awful. That's the day after my birthday. I don't want to be here at 8 a.m., but I guess that's what we're going to do, and I'll be sad. I probably just won't sleep. That's probably what I'll do. 8 a.m. is awful. Goodness. All right, well, if you have questions, thoughts, concerns, let me know. Happy to help. If not, take care.